Welcome back to Physics Fundamentals. In this video, I want to talk about measurement and tolerance. We've previously talked about measurement. We defined it in terms of a very general sense of recording some piece of information. We looked at different standards of measure, different tools that we could use to give a numerical value to various quantities that might be interesting. In this video, I want to address one of the fundamental facts of measurement that makes our lives incredibly difficult. That is that every measurement, well, almost every measurement, is an approximation. Right. If I want to measure, say, the number of chairs in the room I'm in, I can look around the room, I can count all of the chairs, and there's not really any wiggle room on that. Processes of counting usually give us exact measurements, but most anything else is going to be an approximation. There's actually a physical fundamental limit on most measurements we might want to take, where it is impossible to get perfectly precise measurements. That's just the universe we live in forbids it. But even disregarding that, the measuring tools that we use have their limitations. Right? No measuring tool is absolutely perfect. Every measuring tool has some room for error. We call that room for error the tolerance of the measurement. Related to tolerance are a couple of other ideas. Let me get my head out of the way so I can have a little bit more room to draw some pictures here. And the next thing I want to think about is what's called the least count. The least count of a measuring tool is the answer to the question, how big is the smallest subdivision? So here, as an example, I've sketched out a ruler. Let's say that this scale is in decimeters, which is 1/10 of a meter. And if you look, I have 0 and 1 marked out on my ruler, and then there's a whole bunch of tick marks in between. If you count them out, there are 20 tick marks in the space between 0 and 1. So the least count of this particular measuring tool is 1/20th of a decimeter, or as a decimal, 0.05 decimeters. So if I have an object that I'm measuring, and I very carefully line up the 0 point, and it comes over to some spot, let's say here, well, it looks like that's 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75. So the measurement of this yellow bar is 0.75 decimeters. Because the least count is 0.05, that gives us how far off might we be. So I might report that as 0.75 plus or minus 0.05. Right? Worst case scenario, we are off by 1 in the least count. We're probably off by less than that. We are almost certainly closer than that, which is why we report the center value, 0.75, but it gives us our sense of range. It gives us a quick way of describing how well we have measured this. Using more precise tools, we can get a smaller least count, which gives us a more precise value in our measurement, but there's always a trade-off. The more precise the tool you are using, the more expensive it's going to be to manufacture it. So there's a cost there of literal money in getting the tool in the first place, and the more precise your tool is, generally speaking, the longer it takes to use. So there's a cost in labor of how long is it going to take me to get this measurement. Generally speaking, we're looking for a balance point. Get enough precision in our measurement that we know we can use that value well, while not getting so much precision that we are wasting time and we're losing information. That, I guess, leads to the next interesting question of, well, how do we know what kind of precision we need? Sometimes that's pretty straightforward. If you are trying to measure something, if you're trying to cut a rod to fit into a space in a machine, the tool that you use to measure the space and the tool you use to measure the rod should have about the same precision. If you're going to be doing calculations, right, you've measured the length and width of a rectangle and now you need to calculate the area, well then that's where things get a little bit different. In mathematics courses that you've taken prior to this point, you're probably accustomed to your instructor giving you a relatively simple problem, or sometimes a relatively complicated problem, and then giving you instructions like round to the nearest hundredth, or round to 3 decimal places, or whatever else it might be. Which is great in math class, but in the real world, you don't have that luxury. You need, as the person doing the measuring, to understand what that rounding is supposed to be. There are a couple of different tools that are used. One of the easiest is called the significant figures rules, or the significant figures conventions. And that's the one we're going to be using in this course. Before we get into how to use it, I guess, how do you identify it? What makes a figure significant? Well, let's take a look at 2 measurements. I'm going to go to the US customary system for this because I think it makes it a little bit more apparent what I'm talking about, but certainly we're going to be doing a lot more of this in the metric system. So our end goal is to figure out how to round a calculated value. But before we do that, we have to understand what we mean by a significant figure. Right. Sometimes this is also called significant digits, which may make it a little bit more apparent. But we're looking at numbers. How about 20,300 centimeters? And we want to classify these digits as being significant or not significant. Most digits are pretty easy. Any digit 1 through 9 is always significant, no matter what. Zeros are the place where things can get a little weird. If the 0 appears between 2 significant digits, like the 0 right there, we're going to count it as significant. If the 0 appears at the end of a number which does not have a decimal point in it, we're going to say that that 0 is not significant by convention. Right. The way I like to think about that is, well, maybe we had to round. I've written this down as 20,300 centimeters. But if I only have a tolerance to the nearest 100 centimeters, which is 1 meter, then it's not reasonable for me to talk about those 2 zeros, right? I rounded this measurement to plus or minus 100 centimeters. If that's not the case, we have to figure out a different way of notating it. But the convention is going to be, when you see a number written down like this, we're going to assume that those zeros at the end of a whole number represent that we rounded at that point. A number with a decimal point has a slightly different convention. So how about 0.00507 kilometers? All right. Once again, non-zero digits are significant. Zeros in the middle of the number are significant. Zeros at the beginning of a number with a decimal point are not considered significant. All right, those are our placeholder zeros. And so those are not going to be significant. If I modify this value a little bit, in a math class, you're almost always instructed, well, that's how you should write the number. But we could tack on some more zeros at the end of the number after the decimal point. Doing that did not change the value whatsoever. And so we must have had some reason for deciding to do that. Because of that logic, we are going to say that these are significant digits. The zeros at the end of a number that has a decimal point. Those zeros did not have to be there. We put them there anyway. They must be significant. That rule, by the way, also gives us how we could change the zeros over here in the first number to be significant. If instead of writing this in standard notation, I had written it using scientific notation, well, now it is a number that has a decimal point. So if I wanted to include more significant digits, I can put them in after the decimal point, and they follow that rule. And in this case, we have 5 significant digits. Now that we have that rule in place, we can get into the heart of the matter. Propagation of error. If you have approximate values that you're doing calculations on, then what happens to the values after you've done the calculation? Well, there are two rules that we can use. When you are adding and subtracting, you use kind of the easier rule. Adding and subtracting is nice because you can only add or subtract numbers when they're in the same units of measure. And so, comparing where you rounded on the numbers makes a lot of sense. We're going to use what's called the worst precision. The precision is the place value where you rounded. Typically, when you're adding or subtracting, you're going to have measurements that were taken in the same way, so they will have the same precision. But that doesn't necessarily have to be the case. So, for example, let's say that we have something that is relatively large, 306 centimeters. That's just over 3 meters, or in the ballpark of 10 feet. Right, so measuring something that large is somewhat difficult. You have to use a cumbersome device, and you're not going to get that much precision. In this case, we've got precision to the nearest centimeter. And then we're going to shave a little bit off of one end. We're going to shave off specifically 1.5 centimeters. Now, because of the measurement that we took in the first place, having the tolerance of within a centimeter, shaving off a fraction of the centimeter is going to be a little bit weird, right? That's within the tolerance. And so we want to round given the worst tolerance, right? Nearest centimeter is worse than nearest tenth of a centimeter. And that's what we're going to use in this calculation. So sure, if I put this into a calculator, I would get 304.5. But I want to round to that guy. And I will round it and call it 305 centimeters instead. When we're doing basically any other operation, multiplying, dividing, exponents, or roots, we have a bit of a problem with precision, right? If you are looking for, say, the rate of speed that you get by dividing the distance you've traveled by the amount of time that it takes, well, the distance that your car has driven is measured in miles or in kilometers. The time that it took is probably measured in hours. How is plus or minus a tenth of a kilometer and plus or minus a tenth of an hour related to each other? It's really not. And so where you rounded is not something that can make sense using these operations. Instead, we have to turn to something else. Something else we're going to turn to is what we call the accuracy of the number, or more practically, the number of significant digits, the number of sig figs in that value. So if I want to, let's say, multiply, let's say I want to multiply 307.6 centimeters, and I want to multiply that by 0.015 centimeters. Well, 307.6 has 1, 2, 3, 4 significant figures. 0.015 has 2 significant figures. Remember, the leading zeros in a decimal number are not significant. Between these, the worst case is the 2 significant figures. Oops, that's the button I wanted. If you go ahead and put this into a calculator, it's going to give you the result 0.4614. But we know we wanted to round the result to have 2 significant figures. So the leading 0 is not significant. The 4 is significant. The 6 is significant. The next digit was 1, which says round down. But 0.46 is all I get. The rest are not significant digits. And my units there are going to be square centimeters. Again, that's why we have to use the accuracy and not the precision, right? This measurement is rounded to the nearest tenth of a centimeter. This measurement was rounded to the nearest thousandth of a centimeter. Neither of those have any relationship to the nearest hundredth of a square centimeter. And we cannot use where did you round as the question here. We need something else. So this idea of accuracy, how many significant figures do you have? We have 4, we have 2, 2 is worse, so our result gets 2 significant figures. That's how we determine how to round. All right. This is one of these topics that feels really awkward the first time you see it. You spend a little bit of time practicing it, you start to get the hang of it, you kind of forget about it, and then it comes back, and you are a little bit better at it than you were before, and it continues to build. Throughout just about any level of physics coursework, from the fundamentals course through and including some graduate level coursework, these sorts of conventions remain the standard. So it's something that will continue for you. In engineering, it's used occasionally. In other fields, you can sometimes see it. There are a couple of other things, right? Statistics has more sophisticated tools that can be used than this. If you go far enough in your studies, or you go into a different field that relies more heavily on statistics, those are things that might come up in the future. All right. In any event, that's all I have for you on this video. As always, thank you for joining me. I'll see you next time.